Hello, my name is Michael. I'm from RoboBoat Aterkia Diponegoro University team, and I'm an electrical engineering undergraduate student. As an electrical engineering student who also serves as a vice leader in this team, I must fully understand the whole electrical and navigation system of our boat. Therefore, in this video, I will tell you the three main approaches of our navigation development to our boat. The first approach is, I will tell you the brief overview of one of our navigation subsystem, which is the sensor optimization. And the second approach is the utilization of the sensor behind our proposed strategy. And lastly, the third, I will tell you the trial that has been made to test the sensor in two different tasks. Our team at Aterkia 6 Diponegoro will maximize the navigation development with three sensors incorporating the sensing ability of the boat. The first sensor that we use is GPS, or Global Positioning System. GPS used in this boat is GPS here too. The sensor will allow the boat acquiring its latitude and longitude point in real time. The second sensor is magnetometer, also known as compass. The sensor is built and integrated in our main controller, Pixhawk PX4. By sensing the Earth's magnetic field, the sensor will update information on the heading of the boat. Lastly, the third sensor is the accelerometer. The accelerometer will sense and measure the acceleration force acting on the boat in order to determine the boat's position in space and monitor the boat's movement. By combining these sensors, a good navigation solution will be achieved to track the desired waypoint for the boat. By learning from the previous competitions, some improvements are needed to make, especially for the sensor optimization. Therefore, to advance the use of the sensor, we have implemented the boat controller design on the PX4 software. The boat controller has two main blocks. The first one is the EKF. The second one is the position and attitude control. EKF, which stands for Extended Kalman Filter, is very well known for performing the best sensor computation. It is used to fuse all three inputs from the sensors. The filter will produce HRRS, or Attitude and Heading Reference System, Inertial Navigation System, or INS, and reduce sensor noise. By proposing this method, data acquisition from the sensor will be more accurate to process by the controller. On the position and attitude control block, L1 control and PID controller will determine the steering output for the ESC motor. L1 control has presented superior guiding performance on curved trajectories, so adding this method will smoothing this control output. AHRS and waypoint that have been computed from the EKF then will be used to update the waypoint and produce the desired acceleration with L1 control. Looking at the diagram, the function calculate steering to waypoint will call the update waypoint method from APL1 controller libraries, providing it the location that the boat should drive towards. The function update waypoint method on the APL1 controller returns a desired lateral acceleration, which is passed into the mode's calculate steering from the lateral acceleration. Then, the calculate steering from the lateral acceleration sends the desired acceleration to AR attitude control, which uses a PID controller to calculate a steering output. Finally, the steering output is sent into the ESC motor's library using the set steering method and will make the boat stays in the desired trajectories. So, using these couple improvements from the sensor optimization, Aterkia 6 Diponegoro will undoubtedly perform better than the last team. In this section, we have made some trials to test the sensor, both mandatory navigation channel and speed gate challenge. In the mandatory navigation channel, the boat must navigate autonomously between the gates without touching any of the buoys. By looking at the footage, it is shown that the boat autonomously navigates 6 feet from the gate, and by placing the several waypoints, the compass, GPS, and accelerometer automatically sends the navigation information and update the changes. This information will be helpful in the L1 control and PID controller to change speed and acceleration so the boat can stay on the desired path. Furthermore, Based on the GPS data on a graphic user interface, the EKF algorithm proposed in the strategy has successfully made the navigation information accurate. It makes the boat track the actual waypoint smoothly. In the speed gauge challenge, we have made 2 trials to test the sensor and controller of our boat. In the first trial, the sensor has sensed the navigation information accurately, but some oscillations occurs in several trajectories. It is mainly because of the change parameter affected by the water wave. Thus, in the next trial, we have made some improvement by tuning the PID controller of the boat. In the second trial, PID tuning has been executed. It shows that the boat can navigate smoother than the first one. The use of EKF on both missions has successfully affected the navigation process of our boat. Although there is some room to improve, the boat can moderately perform better in navigation in both missions. Therefore, for further development, Aterkia 6 Diponegoro was looking forward to adding more sensors and using a different kind of protocol so more of the tasks could be done.